think about this for a second. Every single time you hit save on a script or, push a Docker container to your home lab or even just back up a family photo, that data physically lives somewhere.
Right. It claims actual real estate in the physical world. It's not just magic.
Exactly. And today we are looking under the hood of those invisible engines of data storage. We're taking a deep dive into the brilliant and sometimes surprisingly fragile strategies used to keep our digital lives from just vanishing into the ether.
It's a fascinating topic, and we're pulling directly from the Professor Messer IT certification trained materials for this.
Yeah, specifically zeroing in on their modules covering storage devices and RAID configurations. And I mean, it's such a great source because it completely strips away all that flashy consumer marketing jargon, right?
Oh, absolutely. We are looking at, ultra-fast marketing buzzwords. We're looking at the functional, physical reality of how a server or a workstation actually handles and protects data on a mechanical level.
So by the end of this deep dive, you're probably going to totally reevaluate how you store your most critical files.
I wouldn't be surprised.
I mean, we're going to break down why that trusty USB flash drive you probably have on your keychain right now is actually a terrible backup plan.
It really is a ticking time bomb.
Yeah. And we'll demystify the literal mathematical wizardry that IT professionals use to rebuild lost data out of thin air when a drive inevitably fails.
But to get to that mathematical recovery, we really have to start at the physical baseline.
Right, because standard memory like your RAM is volatile.
Exactly. Turn off the computer, or if the power gets cut, anything in RAM just disappears. So anything you want to keep has to be caught and held by a non-volatile storage device.
And for decades, the undisputed king of that non-volatile realm was the hard disk drive, the HDD.
The classic spinning rust, as they call it.
Yeah. And the mechanics inside an HDD are just wild when you actually think about the tolerances.
Oh, they're incredible mechanical marvels.
Right, like you have this sealed metal box containing magnetic platters and an actuator arm with a read-write head hovering like microscopic distances above those platters.
And depending on the drive, whether it's the bulky 3.5-inch desktop form factor or the smaller 2.5-inch laptop size, those platters are spinning incredibly fast.
Yeah, the sources mention 5,400, 7,200, 10,000, or even 15,000 revolutions per minute.
And 15,000 RPM introduces massive physical forces. I mean, the heat, the vibration, the sheer kinetic energy inside that chassis is intense.
So why push it that hard? Why make it spin so aggressively fast?
It all boils down to latency, because the read-write head can only interact with a piece of data when its physical location on the platter rotates underneath the actuator arm.
Okay, let's unpack this for a second. So an HDD is basically like a hyper-fast record player.
That's a great analogy, yeah.
The needle physically has to wait for the right part of the song to spin around. So a 15K drive drastically cuts down the milliseconds you spend waiting for, say, Sector 42, to physically arrive under the needle.
Exactly. It minimizes the seek time. But this also brings up the fundamental vulnerability of traditional hard drives.
Which is the mechanical friction, right?
Yes. Moving parts eventually fail. The actuator arm sweeps back and forth millions of times. The spindle bearings wear down. It is simply a matter of physics that one day that drive will die.
Which forced the industry to look for something else for performance-critical tasks. And that's where solid-state drives, or SSDs, come in?
Right. SSDs rely entirely on memory modules soldered directly onto a circuit board. Zero cladders, zero actuator arms, completely non-volatile memory with zero moving parts.
And I think people often compare an SSD to instantly teleporting to a piece of data, but the source material made me think of it differently.
How so?
Well, if a mechanical hard drive is like reading a physical book, flipping through pages sequentially to find a, quote, an SSD operates more like a massive interconnected grid.
Yes, exactly.
The controller can just send an electrical signal down a specific column and row to access any individual memory cell instantly. It doesn't have to wait for anything to physically align.
And that grid layout essentially eliminates physical latency, which makes SSDs exponentially faster.
But there's always a but, right? That raw speed created a massive bottleneck elsewhere in the system.
It did. Because once we invented SSDs that could teleport to data, we realized the existing roads connecting the drive to the computer were just way too slow.
Right. The motherboards were designed for those slower, page-turning mechanical drives. We were using the SATA interface.
Specifically running the AHCI protocol, which maxed out at 6 gigabits per second.
And 6 gigabits was plenty of headroom when we were, waiting on a mechanical arm.
Sure. But suddenly we had SSDs that could retrieve data 10 times faster than the SATA cable could actually transmit it to the CPU.
So we basically had a hypercar stuck in a school zone.
That is the perfect way to describe it.
Yeah.
So the storage industry realized they needed a completely different protocol.
And that led them to the PCIe bus.
Exactly. They began plugging SSDs directly into the motherboard's PCIe bus, which is this massive data highway usually reserved for high bandwidth components, like graphics cards.
Oh, wow.
Yeah, by utilizing PCIe adapter cards, an SSD could commandeer multiple PCIe lanes, unlocking an astonishing 64 gigabits per lane. It fundamentally changed system architecture.
Okay, but I noticed the Professor Messer materials outlined a strange middle ground during this transition. They spent a bit of time discussing the SATA.
Ah, yes, a SATA.
If the ultimate goal was getting to those crazy PCIe speeds, why did the industry even bother creating a miniature SATA connection?
Well, you have to remember, the hardware market was dealing with this explosion of ultra-thin laptops and early tablets.
Oh, right, space constraints.
Exactly.
Yeah.
You physically could not fit a full-size PCIe adapter card or a standard 2.5-inch SATA drive into those tiny chassis.
So SATA mini SATA was kind of the awkward teenage phase of data storage.
That's exactly what it was. It shrunk the physical connector down to roughly the size of a business card, which solved the immediate spatial problem for laptop manufacturers.
But underneath, it was still routing traffic over that legacy 6 gigabit per second SATA highway.
Right. It was smaller, but not faster.
So it was just a stopgap until they finalized the standard we use everywhere today, which is NVMe over an M.2 interface.
Yes, NVMe, or Non-Volatile Memory Express, ditched the old AHCI protocol entirely. It's a communication language built natively around the way solid-state memory grids function.
Supporting those massive parallel data queues.
Exactly. And combining that NVMe protocol with the incredibly compact 22 millimeter wide M.2 physical stick that created the modern standard.
You bypass the SATA controller entirely, piping data straight into the PCI lanes.
Yep. And a modern M.2 NVMe setup easily hits theoretical throughputs around 20 gigabits per second or even higher depending on the PCIe generation.
Now, one vital detail the source is highlighted for anyone actually building or upgrading a system, those little M.2 drives have specific hardware notches carved into the connection pins.
Right, the keys.
Yeah, known as B keys or M keys or sometimes both. And this dictates their throughput capabilities.
And it's brilliant because if you try to force an older SATA-based M.2 stick into a pure NVMe PCIe motherboard slot, the physical keys won't align.
The plastic notches literally prevent you from mismatching the protocol and the hardware.
Exactly. And what's fascinating here is we see the exact same physical engineering philosophy in the enterprise world, but with spinning hard drives.
Wait, let me stop you there. If M.2 NVMe is doing 20 gigabits per second and PCIe cards are pushing 64, why are massive data centers still buying giant spinning hard drives?
I know it sounds counterintuitive, but it comes down to scale and economics.
Okay.
When a cloud provider needs to store petabytes of cold data like massive archival databases or user backups that are rarely accessed, the cost per gigabyte of a mechanical hard drive is still vastly lower than an SSD.
Oh, so they just need cheap, dense storage.
Exactly.
Right.
But to manage giant arrays of these drives, enterprise environments use SAS, or Serial Attached SCSI, rather than standard consumer SATA cable.
And SAS pushes the throughput up, right?
Yeah, to about 22.5 gigabits per second, and it supports complex multipathing.
And the physical connectors for SAS and SATA are just a brilliant piece of design.
They really are.
Because if you hold a SAS enterprise drive and a standard consumer SATA drive side by side, the data and power pins look almost identical.
Right, but the SAS connector is slightly different. It has a continuous piece of plastic bridging the gap between the data and power segments.
So you can plug a cheap SATA drive into an enterprise SAS backplane.
The backplane has a gap that accommodates both, yeah.
But you physically cannot plug a high-end SAS drive into a consumer SATA motherboard.
Yeah.
That solid plastic bridge acts as a mechanical bouncer.
Exactly. It stops you from plugging an enterprise drive into a controller that doesn't even speak the SCSI command language.
Which brings us to a part of the source material that made me seriously rethink my own habits.
Uh-oh. Let me guess. Portability.
Yes. We have all this speed and dense storage inside our servers and laptops, but portability introduces a major vulnerability. The Professor Messer course explicitly warns against using flash drives as archival backup media.
Yeah, USB thumb drives, SD cards, compact flash, they all use EEPROM.
Electrically erasable, programmable, read-only memory.
Right. And the fundamental issue with EEPROM is that it relies on floating gate transistors.
Okay, break that down for us.
So to trap or release the electrons that represent your data, the drive applies a high voltage electrical charge to force those electrons through a microscopic insulating oxide layer.
So what does this all mean? Pushing high voltage through a physical barrier can't be a consequence-free action.
No, it isn't. Every single time you save a document, alter a file, or format the drive, that high voltage slightly damages the oxide layer.
Wow.
Yeah. Eventually, after a finite number of write cycles, the insulation degrades so heavily that the cell can no longer hold an electrical charge reliably.
Wait a second. Almost everyone I know uses tiny USB thumb drives to back up their most important tax documents and family photos. But the source is saying that's a terrible idea.
It is a terrible idea. The memory controller detects that degradation and will eventually lock the flash drive into a read-only state to protect the existing data. Or worse, the drive will simply fail outright.
So you might be able to pull your old files off of it, but you will never write a single byte to it again.
Exactly. And when you combine that finite physical degradation with the fact that USB sticks are tiny, easily lost, and frequently dropped, relying on them for critical long-term archiving is a recipe for catastrophic data loss.
So what does the source suggest for true long-term archiving?
They suggest going entirely retro, optical drives.
Like CDs, DVDs, and Blu-ray discs, it feels like stepping back into 2005.
It does, but the physics make total sense. Optical discs don't trap electrons in degrading oxide layers. A laser physically burns microscopic pits and lands into a dye or metal layer on the disc.
Oh, right. So as long as you keep a Blu-ray in a cool, dark, dry place so the materials don't warp, those physical bumps aren't going to suddenly leak electrons.
Exactly. Optical media trades raw speed and convenience for chemical and physical stability.
Yeah.
They are incredibly reliable for long-term archiving.
Okay, but for active, daily use systems where data needs to be constantly accessed and protected against mechanical failure, IT professionals don't use CDs. They deploy RAID.
Right. RAID, redundant array of independent or sometimes inexpensive disks.
Now, before we dig into the flavors of RAID, we need to address what seems to be the most misunderstood concept in IT, the absolute golden rule.
Oh, yeah. The course beats this into your head. RAID is not a backup.
Hold on, let me push back on this on behalf of everyone listening.
Go for it.
If RAID automatically copies all of my family videos to a perfectly redundant secondary drive, so that when the first drive explodes, my files are completely safe, how on earth is that not a backup?
This raises an important question, and it's why the term redundant creates a false sense of security.
Right.
Redundancy is exclusively about hardware uptime. It is designed to keep the server running and accessible to users when a physical drive catastrophically fails. But RAID mirrors commands instantly. If a ransomware script encrypts your family videos on drive 1, RAID will instantly and perfectly replicate that malicious encryption onto the redundant drive.
Oh, wow.
Yeah. If you accidentally delete a vital database, RAID executes that deletion across the entire array simultaneously.
Okay, I see the crucial distinction now. A backup protects you from your own mistakes, malware, and data corruption because it's a historically isolated copy.
Precisely. RAID only protects you from physical hardware dying. It keeps the lights on.
And keeping the lights on requires choosing the right architecture, right?
Yeah.
Because the course outlines several specific flavors of RAID, balancing speed, space, and safety.
Yes, and ironically, the first flavor offers zero redundancy whatsoever.
RAID 0, also known as striping.
Right. You take a file, say a massive 4K video, and the RAID controller splits it into alternating blocks. Block 1A goes to drive A, Block 2A goes to drive B, and so on.
So you are writing to multiple physical disks simultaneously, which effectively doubles your speed.
Yes, it's built for raw speed.
Yeah.
But the glaring trade-off is that you have intertwined the data across independent hardware.
Meaning if you lose one drive, you lose everything.
Exactly. Every single file spread across that array is missing alternating chunks of code, rendering the entire volume completely corrupt. Zero redundancy.
So if you want actual hardware protection, you step up to RAID 1 mirroring.
Right. You need at least 2 drives for this. Every single block written to drive A is simultaneously exactly duplicated to drive B.
High redundancy. If drive A catches fire, drive B takes over seamlessly.
But the catch is a 100% space penalty. If you buy 2 10-terabyte hard drives for your server, you only get 10 terabytes of usable capacity.
You are sacrificing half of your purchased hardware purely for the mirror, which gets really expensive.
Exactly. In a massive enterprise environment, buying double the hard drives destroys the budget.
Which brings us to what might be the most brilliant workaround in storage architecture, RIR 5.
Ah, striping with parity.
Right. You need at least 3 drives. You get the raw speed benefits of striking data across multiple disks, like RAID 0, but the last drive stores a mathematical parity calculation.
If we connect this to the bigger picture, this parity calculation is sheer genius. It's the mathematical magic we teased earlier.
Yeah.
It relies on a logic operation called XOR. To visualize how it rebuilds missing data out of thin air, imagine a simple addition equation. A plus B equals C.
Okay, so if drive 1 stores the number 3 and drive 2 stores the number 4.
The RAID controller adds them together and stores the number 7 on the parity drive.
Here's where it gets really interesting. If drive 2 completely dies, taking the number 4 with it, the controller doesn't panic.
Nope. It looks at the surviving drive 1, which has a 3, and it looks at the parity drive, which has a 7.
It subtracts 3 from 7, realizes the missing piece of data has to be a 4, and rebuilds it instantly.
Exactly. The data is reconstructed mathematically on the fly. It's basically a way to avoid paying for double the hard drives while still surviving a crash.
It's almost holographic, where the missing piece of the file is essentially rebuilt from the shadows of the remaining data.
It is. The massive advantage of RAID 5 is that no matter how many drives you have in the array, you only ever sacrifice the storage capacity of one single drive to hold that parity math.
But there is a catch, right? Rebuilding that data mathematically takes serious processing power.
Yes. The parity calculation causes a CPU overhead performance hit during recovery. If a drive drops out, the server CPU has to constantly crunch those equations to serve the missing data to the users while you replace the dead drive.
So it operates in a degraded state.
Right. And if you are managing absolutely critical infrastructure where you cannot risk a second drive dying during that stressful rebuild process, you implement RAID 6.
Which just adds an extra parity drive.
Exactly. It operates on the exact same striping and parity principles as RAID 5, but it dedicates 2 separate drives to holding double the parity equations.
Meaning you can have 2 independent hard drives physically fail at the exact same moment, and the server will remain online.
Yes, though you don't gain any additional capacity from that extra drive.
Right. Now, for the home lab enthusiasts or high-end database admins who refuse to compromise on either speed or safety, the pinnacle is RAID 10.
Also known as nested RAID 1 plus 0. You need a minimum of 4 physical drives for this one.
So it's a stripe of mirrors?
Yes. The controller first pairs the drives off into mirrored sets, creating perfect redundant clones. That's the RAID 1 layer. Then it takes your files and stripes them across those independent mirrored sets. That's the RAID 0.
Wow. So you get the blistering read-write performance of strike data combined with the rock-solid safety of mirrors.
Exactly. You could suffer multiple drive failures simultaneously, as long as it's one from each mirrored set, and stay up and running.
You pay a heavy price in raw storage capacity, obviously, but for databases requiring massive input-output operations, it's the gold standard.
Truly. Understanding these distinct flavors fundamentally changes how you design a system.
Well, we have covered incredible ground here. We started with the terrifying physical forces of a 15,000 RPM mechanical drive and the seek time latency that finally pushed the industry toward solid-state grids.
Oh, we did.
We explored how the NVMe protocol over those massive 64 gigabit PCIe superhighways shattered the old SATA bottlenecks.
And we learned why you shouldn't trust your life's work to a thumb drive.
Exactly. And finally decoded the lifesavers known as RAID arrays and that brilliant XOR parity math. The next time you hear a hard drive click ominously, or you shop for a laptop with an M2 NVMe sticker, you now know exactly what is happening under the hood.
You understand the literal mechanics and mathematics keeping your digital life intact.
Before we wrap up, though, there is one somewhat chilling implication we need to draw from the source material.
Oh, this is a good point.
We talked about how USB flash drives use EEPROM, right? And how that insulating oxide layer inevitably degrades with every single write cycle until the floating gate transistors can no longer hold a charge.
The physical limitation of flash memory, yes.
Exactly. Well, the ultra-fast solid-state drives we praised earlier, the M2 NVMe sticks running our operating systems, our enterprise databases, and our phones.
They operate on the exact same fundamental non-volatile flash technology.
Yes. They have 0 moving parts, but they use those floating gate transistors, which means every single super-fast solid-state drive currently powering our modern world is slowly degrading its own oxide layers with every system log, every downloaded update, and every saved file.
Wow, yeah.
They are all silently ticking down to an exact, mathematically predetermined death, where the physics will simply give out and they will suddenly lock us out of saving anything ever again.
It is an inevitable physical threshold.
Something to think about the next time you hit save. Thanks for joining us on this deep dive.